Okay, let's learn about hyperbolas. The first thing I want you to see is what a hyperbola looks like. So here is the graph of a hyperbola. So it has kind of two parts to it. One is kind of looks almost like a parabola going in one direction and then opening up in the other direction is another parabola. So this one is a vertical hyperbola. So it opens up and down. A horizontal one would open to the right and to the left. So there's horizontal or vertical hyperbolas. But it's a little deceptive. It looks almost like a parabola right now, but it actually is not a parabola. If I zoom out a little bit, so I'm just going to zoom out, just take a much bigger view of this. You can see that it doesn't really look like a U there, like a parabola looks. It looks like a V. So the sides, what's interesting, the sides of a hyperbola, we actually use dotted lines, and then we'll draw the hyperbola like inside of those. They hug up to the asymptotes there, and so a hyperbola has actually the sides are kind of flat. They're kind of they're linear almost, or they approach a linear kind of a function. This is the formal definition of a hyperbola. Kind of looks a little bit like an ellipse. I want you to see what this looks like. Let's see. Go to this document. So the definition of ellipse is that the difference, so if I add up, take a point on the hyperbola, measure to focus 1, it's about 13.5, measure to focus 2, it's 5.4, if I subtract the 2, it's about 8. If I move this, you have a little longer there, 15.3, 7.3, subtract it, it's about 8. It doesn't matter where I move this, the difference is about 8 every time. So that's the definition of an ellipse. I also want you to see that ellipse is related to, actually a hyperbola is related to a circle and an ellipse. This is ellipse has two focus points. If I move these focus points so they're on top of each other, that's actually a perfect circle. So an ellipse that the focus points are on top of each other would be a circle. If I stretch it out, the eccentricity of this ellipse is kind of squished. It gets more. But if I were to take it outside of the ellipse, those focus points, they would become a hyperbola. So think of a hyperbola almost like where the focus points are not inside the figure, they're outside the figure. So it kind of has parts going in each direction there. So let's look at the formulas. You'll need to copy these down for your notes. There's some similarities with some of the other, say the ellipses we just learned. So there's a minus sign now instead of a plus sign. You remember with ellipses, it was a plus sign there. Said A is not necessarily bigger than B now, but they're both positive. So with ellipse, A was always bigger than B. That's not true here. This formula has changed slightly. Now it's a plus sign instead of a minus sign. I think that formula is the exact same. We used to call that axis with ellipse the major axis, but now it's called the transverse axis. It doesn't mean it's longer than the other axis, but it does mean that it connects vertex to vertex. In this case, it's a horizontal ellipse because they open to the right and to the left. So the transverse axis connects the two vertice points. So it's a distance of 2a because the distance from the center to the vertex, just like an ellipse, is called a. The distance from the center to the focus is called c. And what's interesting with a hyperbola is c is a little bit bigger than a. With ellipse, a was always bigger than c, so it's kind of in the reverse direction there. We'll talk about how to make this dot box, but if you were to measure the distance from that point to here, it is called b. And we'll talk later about how to get that. One last thing here, the asymptotes, these dotted lines, which we use to draw or sketch this figure, the slope of that, so that's really the slope of those lines, is b over a for every horizontal hyperbola. Good, write down these formulas. I'm not going to talk too much about them. Just write them down in your notes. Again, you can use these. So again, still the vertex is the distance from this vertex to the center is called A. Distance from the focus to the center is called B. sorry, C. That's C. And then if I were to plot these other dots here, the distance from here to here is called B. And so this one is a vertical ellipse because the transverse axis goes from vertex to vertex. That's a vertical transverse axis. It opens up and opens down. And so notice this changed, by the way. It flip-flopped. It's reciprocal. These two changed. These two changed. Here's the big change here. This and this changed. So instead of x squared minus y squared, it's y squared minus x squared. So with the vertical, it's vertical because the y squared term is first. The y squared is positive. The x squared term is technically negative. You're subtracting x squared there. Write down these 5 steps for sketching a hyperbola. Just go ahead and write them in your notes, and we'll use those in just a second. So let's sketch this hyperbola. Just like an ellipse, we kind of start out the same way. We want this always to be equal to 1, so let's divide by whatever that is, in this case 144. And you can use your calculator for this. That would be fine to divide these numbers. They're kind of big. So I get equals 1. Well, that's, I don't need a calculator for that. 16 divided by 144, I think that is, goes in there 9 times, so that'd be 1 over 9. So this is y squared over 9, minus sign there. And then 9 times 16 is 144, so this would be 1/16. So this would be x squared over 16. So we have this in nice, beautiful form here. You see the x squared term is first, x squared minus y squared. Therefore, we know it is a horizontal, sorry, I'm just going to write hyperbola, horizontal hyperbola. So it's going to have this kind of a look to it. It's going to open to the right and to the left. There's going to be some vertex points here. There's a vertex, there's a vertex. This from here to here is called the transverse axis, right? It's horizontal, so this is a horizontal hyperbola. So let's get some graph paper out and go ahead and graph this guy. Some graph paper. And let's start plotting. So the interesting thing here is we're going to plot this just like we do an ellipse to start with. So x is horizontal distance. And so this is, by the way, in the formula, this is a squared. So a would be 4. So horizontally, I'm going to move 4 to the right and 4 to the left. 1, 2, 3, 4. Because x is horizontal movement. This is my a squared, or b squared. And y is vertical movement. So I go, the square root of that is b. So I'm going to go up and down 3 units and make my points. Now, in the past, with ellipse, we've just gone ahead and drawn the ellipse. I don't know if you see it. There's kind of a box there. I'm just going to draw it in temporarily and kind of erase it. There's a rectangle or a box that goes around that hits all 4 of those points. Those points are almost like the midpoints of the rectangle. So what I want you to do is actually fill in the corners there of that box. I call this the dot box or the center box. So I'm filling in, there's kind of a rectangle that those 4 points make. The reason we did rectangles, the second step for sketching an ellipse, is just to, basically, it's hard to draw a smartboard here, but a dotted line for an asymptote, dotted line. It's going to go through the corners of the box. So you don't really have to pay attention to the slope if you just connect the corners of the box. So I'm drawing my asymptotes. I need to identify the vertices. Well, this is a horizontal ellipse. That means horizontal hyperbola. So this point off on the right here is one of the vertices. This point on the left is one of the vertices. If it was a vertical hyperbola, this one would be a vertex and this would be a vertex. And once you've done all that, all you do is sketch the hyperbola. Well, think of this like a fence. It's kind of stuck here, so it's going to hug up to the fence. And hug up, it's like a boundary it can't cross. And here's going to hug up to the fence, and here's going to hug up to the fence. And you've got a beautiful graph there. There's one more thing I could ask, which I could say, where are the focus points? Well, I know they're somewhere in this area, and maybe somewhere over here as well. But I don't know exactly where they are. I need to find that value of c. So I know a squared and b squared. If you know that formula, a squared plus b squared equals c squared. Remember, for hyperbolas, there's a plus sign. For ellipses, it was minus. So this would be 16 plus 9 equals c squared. So c squared equals 25. So c equals 5. You might remember that the formula for the focus points on a horizontal hyperbola was plus or minus c comma 0. So you plot the point 5 comma 0 and negative 5 comma 0. Well, you can just kind of look at it and go, well, I know this is the transverse axis from vertex to vertex. Just outside of there somewhere will be the focus points. It's going to be a distance of c away from the center. 1, 2, 3, 4, 5. 5 units away because c is 5. That's going to be our focus point at the order pair 5 comma 0. Again, you could have just used the formula there. 5 units to the left of this center would be the other focus point at negative 5 comma 0. Let's try one more problem here. So we've got some information, not really an equation. We're supposed to find the equation, I guess, here, right? So let's get some graphic out and sketch what we know, and maybe that will be enough here. So the first thing I see is vertices are at 0, 2, so there's a vertex right there, and there's a vertex right there. Right away, you know the center's got to be there. So from the distance from the vertex to the center is a. So a must be 2. Right away, just from knowing this, we know that a is equal to 2. There's another thing that's given to us here. The asymptotes are y equals plus or minus 2. I think that's supposed to be 2x. There is the equation, plus or minus 2x. So that's the slope here. So if the slope is 2 and the y-intercept is 0, it crosses right here. Slope is 2, up 2 over 1, up 2 over 1. I'm going to make some slope points here. I'm going to go down 2 over 1 the other direction, down 2 over 1, down 2 over 1. And so I can draw my dotted line there. It's one of my asymptotes. Another one has a slope of negative 2 with a y-intercept of 0, so up 2 over 1 the other way, up 2 over 1 the other way, or down 2 over 1 the other way. So we'll plot those points, or draw the asymptotes. The dotted line. It's kind of tough to do with this, but you can get the idea. I know A, but I don't know what B is right now. There's a number of different ways to get this. Some students are very graphical. They can see the vertexes here, and they see the dot box. Like they see that this makes a rectangle, and it goes through the vertex there. And so you've got all the points of your dot box there. And you can draw it and kind of think it through, well, B must be equal to 1, and they've got it. But if you're not like that, that's okay. Look back at your formula for the equation of the asymptotes for, let's see, this is what type? That's a vertex and a vertex. So this is a vertical. It's going to open up and open down from those 2 points. So it's a vertical one. Let's look back at the formulas for vertical. There it is, A over B. So we need A over B is the slope. So if you're a formula person, it would be fine to think of it this way. Y equals plus or minus A over B times X, right? So the slope here is really A over B. The slope of the given equation is 2. So I could set those two things equal. I could say, well, 2 must equal A divided by B, because 2 is the slope, and A over B is the slope of those asymptotes, plus or minus. Now, A is 2, so let's plug that in. So I get 2 equals 2 divided by B. I hope you know what B is, but if you don't, you could cross multiply this and solve it. You get 2B equals 2 divided by 2, and you get B equal to 1. But once you get B equal to 1, we're about there, right? We can just write the equation. Look back at your formula. Go here. Let's see, vertical ellipse y squared over a squared minus x squared over b squared equals 1. So it'll be y squared minus x squared. I know that's because it's vertical. And in the denominators, Y, you're thinking about the a squared term that goes down here. Well, a is 2, so that would be 4, because we're going up and down 2, so that would be 4. 2 squared is how I got that, a squared. B squared goes here, b is 1, so b squared would also be 1, because I go 1 unit to the right in my dot box there. And that's the equation of this hyperbola.